In this module, I'm going to go ahead and start looking at oxidation products. But really the question of this module is, will this acid dissolve this metal? I want to look and see, will these things actually dissolve one another? How do I know? By their potentials. I'm going to see if it's possible to oxidize something. So will an acid be able to dissolve a metal? Dissolve is kind of a misnomer. We say it's dissolving or the metal appears to be disappearing, but really what's happening is the metal's being oxidized. So pictured here is a strip of zinc metal in acid. And we see we see the metal, we see some clear solution, we see a lot of bubbles. What's really happening is the zinc is being oxidized, so it's losing its electrons going into solution as zinc 2+. So the metal appears to dissolve because the metal itself is being oxidized into its zinc 2+ ion. For example, I could put this into hydrochloric acid, and this would be the reaction of zinc metal plus HCl, giving me zinc 2+ and H2 gas. And then I balance it. And of course, I'm so used to doing net ionic equations here. This would actually give me zinc chloride, CnCl2 aqueous, plus H2 gas, if I was writing out the molecular equation. But in this case, the chloride ion is your spectator. And what's actually happening is this reaction here. So acids will appear to dissolve the metal if the acid is able to oxidize that metal. Meaning, if the acid is more willing to be reduced than the metal is. Neutral metals turn into a positive metal cation. Another example we see is magnesium metal dissolving in hydrochloric acid. It's a common experiment done in across a lot of schools. They do like a Hess's law experiment, a calorimetry experiment, and magnesium metal with hydrochloric acid forming magnesium chloride and H2 gas is a common reaction. So again, when does this happen? When it's easier to reduce the H plus into H2 gas than to reduce the metal ion itself. So let's work some examples because again, that's the best way to see this. Predict quantitatively whether 1 molar HNO3 will dissolve gold metal to form a 1 molar Au3+ solution. What do I mean quantitatively? I mean with values. So first I'm going to show you how to do it just qualitatively, meaning looking at the values, seeing if it matters, seeing what's going to happen. But then I'm also going to show you quantitatively what's going to actually happen here. If I've got gold in solution, gold metal is Au solid. And I want to see, will this break down to form Au3+ plus 3 electrons. Now, what I'm going to look up online is the reduction potential. Okay, so what I'm going to look up online is Au3+, or in your textbook, whichever, plus 3 electrons giving me Au solid, and I find the reduction potential here is positive 1.50 volts, which means gold truthfully really likes to have that electron. It really likes to just be in its reduced form. It's a pretty positive number. I look at hydrogen, and if I write down the reduction reaction for hydrogen, again, that is the 2H+ aqueous, gaining 2 electrons, giving me H2 gas. And this is my standard reduction potential that everything else is based on. This is 0.00 volts. Will this be enough to oxidize the gold? No, right? When I look at who wants the electrons more here, I go to the more positive value and I see that this is definitely much more positive than this one. So no, it will not. It cannot oxidize the gold. So, will this be enough to oxidize gold? No, it can't do it. The potential's not high enough to do it. But I haven't discussed every species present, right? I know I've got gold solid in here. I've got H+ in here. I've got NO3- in here. These are aqueous phase. It is aqueous, so I am in water. What about the nitrate? If I reduce the nitrate, could that dissolve the gold metal? I'm going to write this reaction the other direction. And again, the cell potential here for reduction, 1.50 volts. If I look at reducing nitrate, NO3 minus reacts with 4 moles of H plus, gaining 3 electrons. I'm going to form NO gas and 2 moles of water. The reduction potential here is fairly positive, at least compared to hydrogen. It's 0.96 volts, but it's still not big enough to oxidize gold. But I want to answer this quantitatively. What do I mean by quantitative? I mean if I actually did flip around my gold equation. So if this was able to oxidize the other species, that means this would be reduced, and I'd have to oxidize the gold. So Au solid going to Au3 plus 3 electrons. My oxidation potential here would be negative 1.50 volts. Now, for my overall reaction, I'd add these together. Conveniently, they each have 3 moles of electrons in it, so that cancels out. But the overall reaction here, if this did proceed as written, would be NO3 aqueous plus 4H plus Au solid, giving you Au3 plus, NO gas, and 2 moles of H2O liquid. But my potential here would be 0.96 minus 1.50, which would be a cell potential of negative 0.54 volts. This cell potential is still negative. And when you have a negative cell potential, that means it is not spontaneous. If you ever get confused and can't remember, just remember the equation for delta G. Delta G is equal to negative NFE. So we've transferred 3 moles of electrons here. Faraday's constant, 96,485 coulombs per mole of electron, times the cell potential, negative 0.54 volts. Remember, a volt is a joule coulomb. So let me write that in here just so we can see our units canceling. Joule per coulomb. Now, I don't have my calculator in front of me, but when I do this, I've got a negative sign here, a negative sign here. Overall, delta G is going to be a positive value, which means non-spontaneous. So I can look at this qualitatively and say, yep, definitely not going to be spontaneous. But I should also be able to look at this quantitatively. And if I'm given the values, I should be able to calculate whether it will dissolve or not. Let's work another example. Is H plus capable of oxidizing Cu to Cu2 plus? Let's write down our reactions. If I'm looking at Cu2 plus 2 electrons, giving me Cu solid, the reduction potential for this reaction, 0.34 volts. Hydrogen, it's 2 in the wrong spot, sorry, 2H plus aqueous plus 2 electrons. I definitely forgot the arrow in that reaction, I apologize. Giving me H2 gas. Reduction potential here, 0.00 volts. Right now I can look at this qualitatively and say, this is more positive, this want the electrons more, this H plus will not dissolve the copper. What if I want to answer this quantitatively? Well, kind of like we just did in the previous example. If it forced it to happen, that would be copper solid going to copper 2 plus 2 electrons. And my oxidation potential here is negative 0.34 volts. And my hydrogen, 2H plus, gaining 2 electrons, giving me H2 gas. Reduction potential, 0 volts. Overall, the cell potential of the reaction would be minus 0.34 volts. And if I plug that into delta G would be a positive value. So both qualitatively and quantitatively, I can say no. H plus is not capable of oxidizing copper to copper 2 plus. Is Fe3 plus capable of oxidizing I minus? Well, this one's kind of a tricky question. It really depends on what we're looking at here. And I need to pull up the standard reduction potential table because I don't remember all the values off the top of my heart. 1 second, I apologize. Well, first, what I can do is I can think about what is going to happen when iron 3 plus is reduced. One of two things could happen. I could either have iron 3 plus gain 3 electrons, and they do these in successive steps, by the way. Gain 3 electrons. It's not one fell pick up 3 electrons. This would give me Fe solid, which would be a cell potential, reduction potential of negative 0.036 volts. But I could also have Fe3 plus aqueous, gain 1 electron, forming Fe2 plus aqueous. And the cell potential here is what I need to look up because I do not remember, I apologize, is positive 0.77 volts. And then I minus, if I look at I minus, I've got 2 I minus aqueous, gaining 2 electrons, giving me I2 solid, losing 2 electrons. I wrote that backwards. I was writing the oxidation. I apologize. I2 solid, gaining 2 electrons, giving me 2 I minus. That's what I was trying to write. And this is the value I do not remember. So 1 second while I look this up. Trying to find my cell potential table. There it is. And iodine being reduced is a positive 0.54 volts. So quantitatively I can measure in a sec. Quantitatively, I can say that this first reaction isn't going to do anything, right? It's the most negative of it. Qualitatively, I can absolutely say, though, that this can happen. This is a more positive value. So in this case, yes, Fe3 plus could oxidize iron or iodine. It could cause the iron could oxidize the iodine because it's a more positive potential than the I2 going to I minus. So what I've got here is Fe3 plus aqueous gaining an electron, going to Fe2 plus aqueous. Reduction potential here, positive 0.77 volts. This is going to cause the iodine to be oxidized to I minus aqueous, giving me I2 solid plus 2 electrons. And the reduction or oxidation potential here, I flip the reaction around, is 0.54 volts. Overall, if I was to write the balanced equation, I would have to multiply this 3 by 2. Do not multiply your reduction potential. Remember, it is potential energy. It's the potential energy of the system. It's not dependent upon the number of moles of the reactant and product when you're just balancing out between 2 half reactions. 2 Fe3 plus aqueous plus 2 I minus aqueous gives me 2 Fe2 plus aqueous plus I2 solid. And I don't have my calculator in front of me, so 1 second while I try to add this up. 0.77 minus 0.54. The cell potential here, 0.23 volts. And if you're not sure, you can go ahead and calculate delta G. Negative NFE. 2 moles of electrons transferred. Faraday's constant, 96,485 coulombs per mole of electron. And the cell potential, 0.23 volts, and volt is a joule per coulomb. So moles of electrons have canceled, coulombs have canceled, I'm given joules. And if I take that, let's see, -2 times 96485 times 0.23. My delta G here will be negative 44 kilojoules. It is a negative value, which means that yes, Fe3 plus is capable of oxidizing I minus because it's going to oxidize I minus into, it's going to form iodine or I2, but the iron is going to be reduced to Fe2 plus. Is Fe3 plus capable of reducing chromium from Cr3 plus to Cr2 plus? So in this case, because Fe2 plus is reducing something, it means that is this going to be oxidized? Will this be oxidized? Will it give up its electrons to reduce chromium from 3 plus to 2 plus? Fe2 plus forming Fe3 plus an electron. Cell potential here, because it is oxidized, is flipped around, 0.77 volts. Remember on the previous example, right here, I apologize for flipping so fast. Right here, I was showing the reduction potential of 0.77 volts because I was reducing iron 3 plus to iron 2 plus. Now I'm oxidizing iron 2 plus, meaning I'm forming iron 3 plus, so that cell potential got flipped around. And I look up chromium. Chromium 3 plus 1 electron to form chromium 2 plus. The reduction potential here, negative 0.50 volts. Overall, will this happen? If I look at this reaction, add these together, that would be Fe2 plus aqueous plus Cr3 plus aqueous, giving me Fe3 plus aqueous plus Cr2 plus aqueous. The electrons have canceled out. My cell potential here, though, negative 1.27 volts. So the answer here is a giant no. When your cell potential is negative, it is non-spontaneous. Your negative cell potential will lead to a positive delta G. If you don't trust me, let's go ahead and calculate it. Negative NFE, negative 1 mole of electrons transferred. Faraday's constant, 96,485 coulombs per mole of electrons transferred. And your cell potential, negative 1.27 volts, is negative 1.27 joules per coulomb. Moles of electrons cancel, joules can't, or coulombs cancel, or left with joules. Let's go ahead and plug this in. 1 mole, negative 1 mole times 96,485 times negative 1.27. Delta G here, I need 3 sig figs, is 123 kilojoules. It is positive, which means non-spontaneous. Which means no, Fe2 plus is not capable of reducing chromium 3 plus to chromium 2 plus. One more example, is H2 capable of reducing silver plus? If H2 is reducing silver, that means that this is oxidized and this is reduced. So silver gaining an electron, forming silver solid, has a cell potential 0.80 volts. H2 being oxidized to form 2 moles of H plus. And 2 electrons. 0.00 volts. Overall, the cell potential here is a positive 0.080 or positive 0.80 volts, which means yes, this is possible. Again, if you wanted to calculate delta G here, negative, when you balance this out, you're going to get 2 moles of electrons transferred. Faraday's constant, 96,485 coulombs per mole of electron transferred. Cell potential, positive 0.80 volts, which is joules per coulomb. And calculate that out. 2 times 96,485 times 0.8. I need 2 sig figs. My delta G value here is 150 kilojoules. But it is positive, which means non-spontaneous. Or, sorry. I forgot the negative in front. That was a mistake I made. I forgot to plug the negative in my when I was doing it in. I apologize. Delta G is a negative 150 kilojoules. It is a negative value. So yes, it is spontaneous. And because it's spontaneous, that means that yes, this is capable of reducing silver plus.